Hello, good afternoon and good morning if you're watching from North America. My name is Marcus Kremers, CTO of Airborne, and welcome to the second edition of Airborne on Air, where we speak to pioneering innovators. You just saw a small video about Airborne. I saw already a question about the sound. I didn't hear the sound as well, so that's probably a technical problem. Before we go into the webinar, just two remarks. There's a chat function on the bottom of your screen. You can use it if you have technical questions, but also to introduce yourself if you want to the rest of the audience. There's also a button Q&A where you can ask some questions about the content, and maybe we can try to answer them during the webinar. So why do we do this this webinar series? This will be every 3 weeks at 4 o'clock, so stay tuned. We do that because as Airborne, we also like to innovate and pioneer. And therefore, it's always nice to talk to other pioneers and really think about what's the future of composites and what are the cool technologies that are being developed and will come to the market maybe in the next 5, 10, or 20 years. And the second reason is we think composites are very important to address the challenges of society, more specifically around sustainability. And we would like to hear from these pioneers what they think about sustainability and how composites can help. So today we have Kunal Masania, a researcher and professor at University of Delft, Technical University of Delft, also where I graduated. So that's a nice coincidence. He does, I think, really cool stuff, really scientific stuff, and a bit science fiction, really thinking about the future, making the impossible possible. So Kunal, welcome to this webinar. Hi, there you are.
Hi.
And Kunal worked at ATH in Zurich before. I moved to University of Delft, I think, early in 2020. And we are very happy to have you here today. So Kunal, maybe you can introduce yourself very shortly. Who are you and what do you do in composites?
Yeah, sure. Thank you. Yeah, so my name is Kunal Masania. I'm an associate professor at TU Delft in the Faculty of Aerospace. And with my group, we work on additive manufacturing of bio-inspired composites. So what that means is we try to replicate design principles from natural materials into synthetic materials using additive manufacturing.
Sounds good. And to kickstart also functionality of Zoom, we have a small poll that we want to do, where we have a question about the work that you do. So you don't know what kind of poll we are asking, so for you it's also a surprise. So I know you work on bio-inspired and biologically fabricated composites. So I just wanted to ask the audience, what is it actually that you do? And there's some, I think all the answers can be good, but I'm just curious what everybody thinks. So the first is natural fibers and bio-based resins. Second is more to optimize design concepts that mimic designs that you see in biology, so in nature. Third is structures that are actually grown by organisms, by biological organisms. And the fourth is to manufacture structures with additive manufacturing, like the way how nature would build them. So you can now vote on one of these four answers, and then we'll see what the audience thinks. So here we have the answers. It's always a big surprise. Okay, so most people, they think it's about design concepts that mimic biological designs, which I think is a good answer. And the third one is also more about manufacturing. Little people think it's actually grown by biological organisms. So that's clear. So have you anything to comment, Kunal? What do you think?
No, it's a very nice perspective. I like the answers that you picked as selections, because actually we work on all of these things. So some of these things are from my past work, more industry relevant research. Some of these things are things we are working on in the future. So things which are not yet communicated with the world. So things we are still trying to solve problems for. So Yeah, nice question.
Good. I know you've prepared a presentation about your work, so now is a good time to do that and listen to what you have to tell to us.
Thanks. So you should see my screen nicely.
Yep.
Great, thank you. So just to introduce myself again, I'm Kunal. I'm mostly working on additive manufacturing of bio-inspired composites in my group. So our group is called the Shaping Matter Lab. And I'm going to present you a bit of the work we're doing within my group. So to start you a bit about where I am and why am I here. So I'm at the Faculty of Aerospace, and it's a really interesting hotbed because it's full of interdisciplinarity. We work all together with experts in aerodynamics, in stability, in structures and materials, and we work all together towards a vision which will be CO2 neutral mobility. And you see really cool concepts like the one I'm showing you. So this is a flying V. This is something we work on together in the faculty, where we hope that in the future we can bring sustainability to how we have mobility as a society. And to realize these crazy structures, we have a lot of work to do. So these things today remain difficult to manufacture. And a really interesting opportunity is coming from the power of computational design. So there's a lot of really amazing work being done. So I have two examples here. The first is a topology optimization from a group in Denmark. So it's from Niels Age and Ole Sigmund's research, where they used a supercomputer to put all the flight loads that might be experienced by an aircraft wing into a supercomputer and to try to topology optimize what the internal structure of this aircraft part might look like. And it's I hope you agree with me. It's quite beautiful. It's quite organic. The veins inside this this wing concept look really, really amazing. And also, there's really amazing work done from Schmidt et al. So this is published last year. Research to topology optimize this aerospace bracket. So it's quite a famous concept for people who work on additive manufacturing or topology optimization. It's a GE bracket. And here you see really amazing stress lines flowing through the structure in quite an organic way, where you see the density changing locally. And the challenge today is that these remain unmanufacturable. It's very hard to go from the traditional composite manufacturing process we have to these kind of topology optimized and structure optimized designs. And when I look at them, I immediately think of natural materials. So that's what we do in our research. We also look at how natural materials structure themselves. So here are two nice examples. One is wood on the left. So for those of you who are in the Netherlands right now, this is actually how the trees in Netherlands look today, because it's windy like hell today. And also bone on the right. And if we zoom in a bit on bone, and this is also common for wood, you notice something interesting about the structure. And what you notice is that there is a hierarchical structure. So it's structured at a very simple structure of a molecule, very simple chemistry. But by utilizing structure at multiple length scales, you start to build up something which is macroscopically recognizable and has very high structural efficiency. And some of the cool principles of natural materials are that they don't rely on chemistry. They rely on the structure of the hierarchy to give their high mechanical properties. And also, there's a lot of details beyond just fiber orientation happening inside these structures. So they readily incorporate different density of fibers, different orientation, also matching porosity into the structure. And even beyond that, they do really amazing things like being able to reconfigure the material. So as the demand of the structure is changing through a lifetime, then the structure is adapting. And these are inspirations that we're really excited about, maybe trying to adapt into our manufacturing principles for the future. So what we try to do is we try to adapt their manufacturing principles and structural designs into things that we want to build in the future. So in my group, we work on three core pillars of research. So the first is that we try to apply the natural design principles of biological materials into synthetic materials. And here in the gray, actually behind, you see on the top, you see images of biological nacre. So this is a seashell. at 3 different length scales, and below it you see the synthetic version that we make. And what's special about our material here is that we can build at the same length scale as the biological one, so we can study directly the design principle that nature is using, and we do it with synthetic materials. So actually our material is as good as carbon fiber composites in terms of strength and stiffness, even that we build with nanoparticles. Then I work also in our group a lot on biologically fabricated composites. So we approach this from 2 different avenues. The first is top down. And what I mean by that is we use wood or we use natural plant fibers, and we process them into something that is more recognizable for us as composite manufacturing specialists. So we make semi-finished materials, which can be then processed into structural composites. And here, to give a small example, we can make composites which have stiffnesses up to about 70 gigapascal and strength of about 600 megapascal. So these are better than conventional metals, better than glass fiber composites, as well as being much more sustainable for the future. And we also work on aspects which are from bottom-up fabrication. So we try to start with their basic building blocks, and we try to let nature do the work and structure the material for us. And the last pillar of our group is digital fabrication. So we try to use data to inform the manufacturing process. So there behind in the picture, you see a 3D printer. And actually, the topic that I would like to tell you today is one of our approaches, how we try to leverage shaping freedom to get high mechanical properties for composites using 3D printing. So I want to introduce you first to the problem. So if I show you the plot on the right side, what you see is a plot of specific strength versus specific stiffness. And what you notice is that polymers are quite weak and quite low in stiffness compared to traditional composites. So even with the shaping freedom of additive manufacturing, we still have a big gap to bridge if we want to compete with traditional engineering structural materials. And typically what people do with polymers is try to avoid anisotropy by trying to have high temperatures in the build volume and reducing molecular orientation during 3D printing. And we thought, well, instead of trying to combat this problem of 3D printing, why not try to use it as a feature? So what we came up with was the idea to print a liquid crystal polymer. Liquid crystal polymers are a hierarchically structured material. So you have a very simple molecular building block, and these are very short chains of a polymer. And they're locally arranged as a nematic domain, which is isotropic as a global oriented material. And they have a very special trick to them, which was established and well known from the 80s. And that is that when you apply heat to thermotropic LCPs and you apply shear, that you can create orientation in the materials. So here I'm just showing some logs in a sea, and you can see through the constriction they orient. And for us, we hope that with the printing, similar approaches can happen. And what we were able to do is we were able to take a material which is having similar properties to traditional polymers, and through the hierarchical structure and orientation during 3D printing, we're able to elevate the mechanical properties. So these red dots indicate where we can get to. And so you see here for parts or for lines, we get quite high mechanical properties. And this is quite astounding because it's only a polymer, it's only a plastic, but just by molecular alignment, we can get something which is outperforming glass fiber composites by quite a lot in terms of strength. And it's about 10 times stiffer and 10 times stronger than PEEK as a raw material in the end. And we can really utilize this shaping freedom that you can get from 3D printing. So here is an inspiration. So it's the example of wood. And what we can do is we can follow stress lines around the hull. But as you might know from other composite manufacturing technologies, that you have to change the spacing of the lines locally, so you cannot fill with material. Whereas in our case, because we print a polymer, the polymer is self-assembling, and we have really building blocks at nanoscale. So we can easily change the density of our lines around hulls. And what this means is we can go from something which is quite low in strength and stiffness from the isotropic material into something that becomes very, very stiff and very strong in the end. So we're talking about open hull strength of around 370 megapascal and stiffnesses of around 25 to 30 gigapascal. And I just want to show you another interesting example. So we've done an optimization for fiber path trajectories. So here you see a typical plate, and we want to analyze a problem for buckling. So when the plate will lose stiffness when you apply a compression load. And here what I show is the enhancement of buckling load with respect to how much curvature you give, so how much shaping freedom you add to this plate. And I also indicated here below typically what happens with quasi-isotropic laminates or for tape laying, which is today current state of the art. And what we notice is with LCPs, you have a much higher shaping freedom. So you have a curvature of 500, which is way off the chart in this case. And it seems to indicate that even that we have a less performant raw material, just by having more shaping ability, we can take on other types of application where traditionally we were using more energy intensive materials. So this kind of leads to the idea of being frugal with the material we have, using it only where we need it in the right orientation, and therefore using resources to a much lesser extent. This work was published in 2018, and 2020, a startup was formed from our old research group. So they're called Nematex, and they've been pioneering the industry application of this kind of 3D printing process. So I want to show you some of the parts that they've been manufacturing. So they've been manufacturing for industrial applications. So you see some examples there. They've also been manufacturing for aerospace components because the material has really high thermal stability and really high chemical resistance as well, and also for the biomedical sector. Last year they won the Formnext Startup Challenge, so I'm really excited for them because they've had a really amazing start to this journey. And last year also they won a grant to send the material to the ISS. So the idea is that we send samples to space. They will be conditioned outside of the International Space Station, and then we would retrieve them to understand how the properties are going to change due to this low atmosphere and also UV degradation from being in space. So for me, it's really insane, and it's the perfect example of circular material, because anything you send to space has to be reused and used again. And so it's an opportunity where we can, in the future, maybe 3D print things, and then at end of life, we can chop them down, reproduce filaments, and reprint new structures. And from the early experiments we've done, we found that up to 5 times recycling, you don't really lose any mechanical properties from the material, which is really, really nice.
Good.
So with that, I'm already at the end. Sorry, I took a bit longer. So I couldn't tell you everything I did, but please look at our website and you will find more information on the other research that we are doing.
Thanks.
Yeah, and thanks. Sorry for taking so long.
No, thanks, Kunal. That's perfectly fine. So I have one question there. So to understand it right, you use LCPs, and during the printing, I guess what you're saying is you orient the molecules in a way that they become like fibers. Is that what you're doing? But it's not really like a fiber.
That's exactly correct. So on the molecular scale, they orient to the direction of the 3D printing. And if you don't cool down the prints, then you go back to an isotropic material. And if you cool down the prints quickly, then you can preserve the anisotropy inside the structure.
Okay, so it's heating during the printing and then cooling down to freeze, let's say, this orientation. And how far is this, if you think about making this on, let's say, larger scale, is it difficult to do, or what are the technical challenges to scale this up?
So the material was developed in the 80s and already has a lot of commercial applications. So in fact, all of you that has a mobile phone, you have LCP with you, because it's used a lot in the electronics industry as a cable connector for solder reflow processes. So it's a really good, well-established material. So we don't expect problems for scalability.
Good. Okay, I want to move to the next subject, which is about sustainability. And we also have a small poll for that, for some interaction with the audience. So the first question is, are composites the solution to fight climate change? Yes, because lightweighting is essential. Not yet, because carbon fiber is too energy intensive. Kunal, you also mentioned this already. Renewable energy is much more important than composites. And yes, we need everything that contributes, so you can vote. There's a second question, and actually if you scroll down, also a third one. How to make composites sustainable? Well, lighter is always sustainable. It's about recycling, very important in composites to make this better. Bio-based composites is important, or biodegradable composites, which are of course not the same. And what's the most important challenge at this moment for sustainability? Recycling, using biodegradable fibers, changing the certification process, if you think about sustainability, production cost at scale, or limited properties compared to conventional manufacturing. So you can vote, and then Kunal will try to address the results. Unfortunately, Kunal, we cannot vote ourselves. That's,
I was trying. Yeah, then I can pick the answer I want to tell. Yeah.
No, that's not possible. Okay, so it's interesting because we asked this also the first webinar, and the results are different. So it really depends on the audience. So what do you think about the results?
Yeah, so for the first question, are composites the solution to climate change? It says yes, we need all technologies that contribute, and there I agree. So in the Ashby chart I showed in my work, you saw that composite materials are still the stiffest and strongest by weight materials that we have. So it would be silly to neglect them for applications that we have mobility, where we want to move things efficiently. Yeah, having said that, I think we need to use the right materials in the right applications.
Yeah. And I see the rest of the answers of 2 is about recycling, which is, I think, right. Composites are good, but we can do better in things like recycling compared to, for example, metals. The most important challenge is, again, recycling and production cost at scale, which is, I think, in many cases for composite, the challenge how to make it more efficient and affordable. That's what we try to solve at Airborne. So that's our take at this. So I'm looking to the time. Let's go to some challenger questions. And the first one is by the speaker of the last webinar, Riley Rees. So either Riley is in the webinar or we can play his pre-recorded one.
Also, I've looked a bit at your work online, and I'm intrigued. And as we were kind of looking at consumer space, you're clearly looking at medical and have a number of opportunities there. And I'm wondering, what do you see as the biggest challenges to get composites into medical? Is it like the barrier of having a new material that you're trying to introduce, or is it the barrier of having a completely new process, or maybe a bit of both?
Yeah, so this is a great question from Riley. So I think he picked up on a recent publication we had about biodegradable polymers for implants. To him, I would answer that when there is enough application relevance, then there's always a way. So it's definitely a long process. We see with other companies trying to commercialize 3D printing for medical implant devices, and this is a long process. So I think for any startup, they don't typically start with this application in mind, but it's their long-term vision to do that. And recently, actually, what I see is a big shift from traditionally what we've been doing is trying to implant bio-inert things, so carbon fiber composites that don't react with the body, into things which are actually working with the body. So we're moving towards technologies such as magnesium implants that can encourage bone regrowth, for example, or even the work which we published, which is a biodegradable stent, which disappears by itself. So you save a second operation from the patient by the need to remove it. So okay. That's where I see the exciting opportunities in the future.
Good. We have also a question from Mustafa Ranjbar, who wanted to ask a question. So can we put Mustafa on the screen? And you'll have to unmute yourself.
Yes. Hello.
Hi.
Hello.
Okay, thank you, Kunal, for your nice presentation. Actually, I am working like you, leading a group of researchers, and we are doing research on bio-inspired mechanical metamaterials. So in various fields, actually. So my question, actually, I have a question from you, but shortly I want to say something to Marcus. Actually, there are some specific materials like auxetics that you can change their mechanical properties rather than changing the material. So by changing the geometry of the structure, you can change the mechanical properties. So in some places, they have advantage to composite because they can easily be printed and produced.
Good.
So, but I have a question from Kunal that about, do you have any idea about the animated materials? There are new generation of materials. And I have got really interest to work on this area because there are one stage more than auxetic, and they can adjust themselves according to the situation, Actually, do you have any idea? Have you done any work or something like that?
Thanks.
Thank you for this question. So, yeah, this concept of animate materials is it's emerging in the scientific community since the last few years, and it's really accelerating. And it's the ambition of scientists to try to create materials which are reacting with the environment they are in. We are working on it, and I hope this year that we can share some of the results of what we have done. Yeah, I hope you watch this space for the surprise of these results. Yeah.
Good. We also have a question, and Lara will ask the question.
Yes, it was an anonymous question, so I'll put it forward. Kunal, how far have you got towards commercialization?
Thanks a lot for this question. So as a university and as a research group, we're in the business of generating new knowledge. So we want to progress what we know as a society. And so the commercialization work is I rather leave to the partners and to the startups that we work with. And there I would invite Raphael Heap, if he's on the chat, to join the webinar, and maybe he can mention something about commercialization.
Yes, good afternoon.
Hi.
Hi, Kunal. Hello, Marcus. Thanks for the nice talk and the question. As Kunal mentioned, at Nematex, we have recently started to commercialize the technology using LCPS. And what we can offer at the moment is we print or we do prototyping services for our partners and create our own materials. That's the current status we're in, yeah.
So it's commercially available.
Exactly, yeah. We're not selling materials yet or any hardware, but we do prototyping services and work our way to more technology development until we have more products available.
Good. It's probably not so easy to take such a novel technology to commercialization, but that sounds like you're taking the first step. So that's very encouraging to see. Thanks, Raphael. Yeah, we're through the time. We have 30 minutes, so it's fast-paced. So thank you, Kunal. There's one thing I want to ask you is for the next webinar, we have 90 labs, Yannick Willemin, on the 1st of April. And I would like to ask you, what kind of question do you have for Yannick?
Sure. Yeah, first, I just wanted to say thank you for having me. It was really nice to talk to you. And to Yannick, I want to tell them first congrats, because they're doing really amazing things at 90 Labs. And the question which I was wondering was that they have a very nice workflow for design of structural parts. But now more and more, we need to start to consider end of life cycle and recyclability. And so my question is whether they consider this at the design phase already, and whether they have ambitions to do that if they do not.
Good question. Something to think about for Yannick in the next 3 weeks. So that's good. I have the next announcement for webinar, so that's the one after with Yannick, that's with B-Comp, by coincidence also from Switzerland. So you're all from Switzerland, all these smart guys. So that's the 22nd of April. It will be announced soon. So that's the one following up afterwards. So Kunal, thank you very much. It was very inspiring. I liked your really forward thinking and a new way of thinking about how to do printing with these liquid crystal polymers. Very interesting. So thank you very much. Thank you for the audience. It's also available on YouTube if you want to watch it later. And see you next time. We have a short poll of feedback, how you enjoyed the webinar. So please fill it in and hope to see you next time. Thank you very much.
Thank you.
Thanks.